before introducing Dr. Halperin, I want to begin on a slightly sad note because on March 1st, 2022, we lost Peter Carr. And he was not only the chair of NYU School of Financial Engineering, he was a prolific contributor to options theory. But even here at FMI Tech, he was on our advisory board. And personally, he was a great mentor and friend to me, a very genuine human being. And so deep and broad was his knowledge that he could discuss quantum field theory and finance for hours with me without any formal training in physics. And he particularly enjoyed attending this webinar. And the characteristic feature of Peter was that he would keep asking questions until he had understood something. So in his memory, hopefully we will maintain the same level of curiosity, optimism, and relentlessness in the pursuit of knowledge. Moving on from that sad note, I'll introduce Igor. Igor is another prolific name in the field. Currently at Fidelity Investments, he has been served at NYU, JP Morgan, and Bloomberg, and published numerous influential papers and books, including the widely referenced book Machine Learning in Finance. And he has done truly pioneering work in reinforcement learning, econophysics, and constructed possibly the first truly non-perturbative model of financial dynamics, which is now true in more ways than one. And he was awarded the prestigious Buy-Side Quant of the Year this year for his stellar work in RL, and is an inspiration to us physicists and other quants in finance. And over to you. You can go ahead, Igor, with your presentation.
Thank you very much, Ivan. It's really a pleasure to be here among fellow physicists. As you may know, my background was also in physics, and more specifically, what I did was non-perturbative QCD. And that's why I love the word non-perturbative, first of all. And I was very happy when I found something, as I hope I found something relevant for these ideas and methods. Let me share my screen. And in addition, the other part of this story is that, I was very much into instantons when I did my PhD. Even though I never wrote any papers about instantons, I spent lots of time looking into that. And when I just started my first project in finance, it was at Bloomberg. I was asked to pick some model, credit model for Bloomberg and implement it for the system. So it involved some research. And the first thing I thought about credit defaults, I thought, oh, they should be due to instantons. Not because of any deep insight, but simply because that was the only rare event that I was familiar with. So I got this idea right immediately after hearing about corporate defaults, but it very quickly faded away because, as you know, for instantons, you should have some nonlinear potential, like periodic potential, or potential with multiple minima, and there was nothing like that there. And so, all these models were linear models, and no hints on anything vaguely resembling instantons. So I dropped this idea, but it reemerged surprisingly much later. And the circumstances how it reemerged were also funny. I was actually working on the course, and Peter Carr was my employer at NYU, where I created a course on machine learning in finance, and then also in parallel a Coursera course on the same topic. And my plan was to work on reinforcement learning, but at some point, I didn't have data to train my algorithm for reinforcement learning for portfolios, and I got this idea that maybe we can apply similar ideas to the market as a whole, and envision a collective role market participants as some sort of a collective bounded rational agent. And this brought me to this idea. So like after that, by looking differently at the same thing, like then it clicked, and then I found this non-linearities. And like the few other papers were trying to generalize this and develop it further. So as I mentioned to you, you gave me a tall order. You mentioned that I built a model of model of the market, and exactly at that time I was trying to finish this paper that I finally finished yesterday. And because that paper was about the market, the other paper was kind of illustrated with the ideas of calibrating the index, but it was about single stock, essentially. Okay, so this is a long introduction to the topic, right? So I just utilized slides that I used for more general audience. I hope it will be okay. General audience usually doesn't know what non-perturbative stands, so I used to start with these two questions, which I used as preamble for my presentation. So question number one, where are all non-linearities in finance? And question number two, why we use equilibrium models? So the framework that I'm going to present is trying to answer this question, or we start to answer those questions using combinations of methods and insights from both reinforcement learning and in physics. I use the word quantum physics because people know more what quantum computing, but actually it's quantum mechanics and quantum field theory. All right, and the key role will be played by money flows in the market and the price impact. And there is also this great quote, which I really like from Keynes here. So first about market flows. I kind of came up with those ideas on the theoretical side when I tried to understand what my formulas implied, but around the same time, there've been these two very interesting papers about money flows and the impact on asset price dynamics. The first paper by Gabex and Kojin, and the other one by Jean-Philippe Schub, about the inelastic market hypothesis, how flows into the market and impact returns. But just to give you an idea about the size of the effects, right? So this is the curve that shows cumulative flows into equity, bond, and hybrid funds over this period of time. And you can see that it's almost a linear slope with that much money coming into the market every year, which constitutes about 1% of the market value of S&P. So the question is it a small effect or a large effect? And from physics, we know that sometimes the effects can be numerically small, but extremely important qualitatively, which I think is the case here. All right, now, how reinforcement learning ideas enter here. We can think of market dynamics as some sort of a control problem where we put this is what I mentioned before, this idea that I had when I was working on that course, that you can put all investors into one sort of a collective collective agent on one hand, and on the other hand, you will have the market, and then this setting would exactly correspond to the setting of reinforcement learning problem, which is the problem of optimal control, how it's formulated. So it's a problem which involves sequential multi-step decision making, so that at each step the same exchange of information flow and other things happen. So the first, at each time step, the investors, they get information from the market through vector of prices and any other information. And then upon receiving this information, they trade. So they invest or they trade in or out, which is denoted here as this trade AT. So there is a two-side, two-directional exchange of inputs and information here, and the objective of doing that is encoded here in rewards. So upon taking action, trades A in state S, agents receive rewards, which is reward RT, which is the function of both these guys, so that the ultimate goal of the agent is to maximize the total expected rewards. And this is the same thing as the problem of dynamic optimization, but in reinforcement learning, we take usually more numerically based algorithm to solve exactly the same problem directly from data. Now, how it connects to these things, which I just mentioned here, it connects at the level of, we have to define how agents trade in response to receiving information. And this can be encoded into this simple discrete time dynamics, which is shown here. So what is this? It's a discrete time portfolio model. You can think of, actually this formulation applies for both individual portfolios and the whole market portfolio, but here I use it for market portfolio. So X will be the total capitalization, vector of total capitalization of relations of all firms in the market. And the dynamics that is implied by these equations is shown here. So what happens at each time step, T to T plus delta T, first you have the vector of asset values X, and then investors decide about new money flows. So this amount, this whole amount, is a vector of money flows at the start of this period. And the way I define it, so you see that A here is defined as the ratio, as a rate of change, right? So assuming that this is a deterministic function, which is some sort of a decision of investors, this would be the new instantaneous value of assets. And then, so it's a deterministic part of this dynamics. And then it grows at the rate of R. So that the value of assets at the end of this interval would be given by this expression. So an R here will be a stochastic rate of returns, which is given by risk-free rate plus some combination of signals, whatever they are. I don't explicitly use them. Plus, this part is important. This is the impact function. So that's the impact of trades brought by external investors. And finally, there is a noise floor. Right. So what we need to complete specification of model, and here is the reference to first reference to this formulation. So what we need to complete the specification, we need to define the law for this rate and the law for this function. And this is what I'm going to do next. So what I do next is first I reduce this thing to single stop formulation. So this is the scalar version of the equations that I just showed. And now what like simplest choice, because we don't know this function is unknown, but we assume that this is a function, this rate of money flows should be a function of either asset values as shown here, or maybe changes of asset values as shown here. But we can start with this specification. So if we start with that, then we can write down a general low order Taylor expansion and use it for this function around some maybe 0, right? And use it as a specification of your money flow rate. So that's part number 1. And obviously these coefficients, they can be functions of slow weighing functions of other market variables, but here I keep them as constants. Okay, the next part is specification of this price input function. So the simplest choice would be just to assume linear specification with negative sign here, which has a meaning. I'll explain shortly that. and why I choose this negative sign. But the first observation is that if now you use these specifications, this one and that one in these equations, substitute them into them and take the continuous time limit, then you will end up with the diffusion of this sort. So what's interesting about this diffusion is nothing interesting about the volatility term. It's just the standard log normal volatility. The interesting part is here. And what you see here is the drift is a nonlinear polynomial of the state, variable x. So x is the asset value, or you can treat it as maybe single stock price, something like that. So the drift is now cubic polynomial, and all the coefficients which enter here can be expressed in terms of the original coefficients that I showed you in the previous slide. So this formulation, we call it QED, Quantum Equilibrium Disequilibrium Model. It's a model of an open market with market flows and frictions. And here's the reference. The paper was published in Physica A last year. Now, few interesting observations about that. So if you just take the limit when parameters, so you see that there are a few extra parameters here relative to the geometric Brownian motion. But if you take the limit when parameter G and kappa, G and kappa also enters here, when they go to zero, then you will recover the geometric Brownian motion model. Right. Now, what's the meaning of this? Coming back to this impact function. So, what was the meaning of this function? Is that I just wanted to encode a negative long-term impact on prices when there are lots of investment into a given asset. However, this specification might miss something. It can only capture the very long-term effect of new money when there is lots of investments, right? But what it would miss is the kind of momentum-driven effect when the stock performs well. It usually draws some new investments in a stock which drive returns even higher. So initially, the price impact should be positive rather than negative. It can flip to negative when total investments are exceeding certain boundaries. And this is exactly what can be achieved with a different input function, quadratic function, this time of the input. This function would implement this dump money effect of which I just mentioned according to this paper. Now, but the interesting observation is that if you use now this quadratic input, then you can take a simpler control. So I showed you control, which was the quadratic function of the state variable in the previous slide. But now you can say that if you have quadratic input, you can take linear control and still get the same QED dynamics, which I just showed you before, with just different parameters. All right. So we can conclude that this nonlinearity of the drift is kind of robust. And actually, I believe that any nonlinear model of this sort, which would take into account money flows and price input, would have at least like cubic polynomial complexity here. So it's kind of minimal model of this sort. All right. Now, what's like few things which are also of interest regarding this specification. One of them is that you can view it as a particular case of what is called in mathematics ethos diffusion. Right, so ethos diffusion is just the general diffusion with some drift function and some volatility function. And clearly, this is a special case of this. But what's more interesting, especially for us as physicists, is that this is a special case of more general Langevin dynamics. And you probably all know the Langevin equation, which was proposed by Paul Langevin in 1908, which generalized Einstein's theory of free diffusion. So Langevin extended it to diffusion of a Brownian particle in potential field. So now, if you look at the Langevin equation, this is actually not the most general form of Langevin equation. This is what is called overdamped Langevin equation. If you compare this with the previous formula here, then you will see that actually it's the same, but it gives a meaning to the drift. So drift is not just a f function of state, but it's rather negative gradient, right? So negative gradient, the most classical example of a potential in physics is, of course, the harmonic potential. And as we all know, this is the potential. You put the particle here, it relaxes to the bottom of the potential. So it's an example of a stable dynamics, right? Now, but kind of trivial statement, but apparently it was totally overlooked anywhere, is that you can take the geometric Brownian motion now and also interpret it as a Langevin equation. But the critical observation will be that, you know, if your drift is positive, then your corresponding potential will be of this form. And the critical part is this negative sign. So the potential now looks like that, and it shows unstable dynamics. So when we talk about unlimited exponential asset growth in standard mathematical finance models, actually what it implies is something completely different. It implies unlimited fall in this potential like that. Which like when I realized that, it kind of brought to me analogies with one of my favorite sci-fi books, which is shown here. I have a non-technical paper which talks about its similarity, but I want to save time and move forward. So this QED dynamics can also be viewed as a particular case of Langevin dynamics. And clearly, remember, we had the cubic polynomial as a drift, which of course immediately translates into the fact that the potential itself should be quartic polynomial. And quartic polynomial can have different shapes, which are shown here. Right. Now, the most exciting part, instantaneous. So in physics, we know that many systems with nonlinear potentials, with potential barriers, they have instantaneous solutions. Instantaneous were invented by Alexander Polyakov at Princeton University. And there is also a version of this which actually is more relevant to describe what I have here. It's called balances, which are proposed by Coleman and Cullen in this paper. But actually, instantaneous were invented by George Gamow in 1928. He didn't call them instantaneous. He tried to explain the alpha decay, but essentially, as physicists, some physicists know, it's exactly the same thing. But I just wanted to illustrate what's happening here for the benefit of those who are not familiar with instantaneous. So instantaneous is essentially like an event when you have a potential well with multiple barriers, and you have multiple barriers, and due to fluctuations, which can be either statistical fluctuations in classical system or quantum fluctuations in quantum mechanical systems, either way, due to fluctuations, what can happen is that the particle, which is initially located at near the bottom of the local minimum, can hop over this barrier and find itself on the other side of this barrier, right? And then, depending on what happens here, whether it can continue the slide, if it's unlimited potential, or maybe find itself in another local minimum, maybe even the global minimum. All right, but here is my popular science illustration of how instanton transitions can be visualized. So this is how Harry Potter and his friends were entering the platform number 9 3/4. So you see that they take a run, so they require kinetic energy, and then they overcome this potential barrier. All right. Back to the origins of instantons. So as I mentioned, George Gamow actually discovered essentially equivalent of instantons in quantum mechanics when he build a theory of alpha decay, which is the spontaneous decay of alpha particles, which are 2 protons and 2 neutrons by some heavy nuclei. But very interesting question, which I was asking myself many times, like assuming that we would not know that, how would a statistician explain the alpha decay? So most likely they would say, okay, this is a rare event, it is a Poisson event. So, we would probably model it as a Poisson event. We could even fit, if we wanted to be sophisticated, fit intensity of this Poisson to properties of nuclear. But the question would be like, would it really explain anything or not? And I'm convinced that it would not explain anything. It would be purely descriptive approach, right? But nevertheless, many papers in quant finance, that's exactly what they do, right? People start with math rather than physics, and they say, okay, we consider XYZ process because it fits market data better, right? So to me, it sounds like my approach. So, we rather want to explain things, and the only way to explain things is to come up with either physics-based or what other people call structural model. Right? So now I go back to question number 1 and question number 2. So question number 1 is, where are all non-linearities? So in physics, we know that all interest in physics starts when you have nonlinear systems, right? And nevertheless, all classical financial models are linear models, right? So sometimes non-linearities arise, but in the context of pricing, not in the context of building fundamental model for the underlying, right? So, and on the other hand, like machine learning approaches, they usually operate with highly nonlinear models, but somehow in kind of fully uncontrollable ways. So the question is like, what is there any mid-ground, right? So the QED model that I just outlined to you actually suggested that it should be particular nonlinearity of the potential, which is the quartic nonlinearity, right? Which can capture the effects that we want to capture. All right, question number 2, why we use equilibrium models. So if you look at CAPM, so what CAPM tells you is CAPM gives you the relation between returns of individual stocks as a regression on returns of the market, right? And some residual, right? But like, especially if you think of it as a kind of, think of it as a Gaussian distribution. So this is a setting of people usually think of it as a mathematical regression, but if you think of what it implies in physical terms, it means something weird, I think. It means that like these guys should somehow equilibrate before impacting this guy. And I have no idea how it can happen in reality. None. Right? And on this count, I also would like to bring this quote from this book, very nice book. This guy, Joseph McKenna, right? He said that there are at least 5 long definitions of equilibrium in economics and finance. And the first 3 definitions would be correct were market stationary, but economic processes are known to be non-stationary. So the intermediate conclusion from all of this would be that we would like to have like a model with nonlinear dynamics and generally non-equilibrium dynamics, which would be similar to this framework that I just showed, this QED framework, but hopefully a little bit analytically more tractable. Question is, can we do that? And the answer is yes. My answer is yes, we can do that. And it's possible to kind of simplify it somewhat. But for this, we have to dive first into quantum mechanics. And there are a few easy steps which are done here. So what we do is the following, what I did. I started with the Langevin equation for now, this time for log returns. Log returns are defined as here. All right. And so for now, we can keep it as a kind of general Langevin equation with some nonlinear potential. Right. So if you have this Langevin equation, then you can write down the corresponding Fokker-Planck equation, which is probabilistic equation describing the same dynamics in different language. in terms of probabilities of transitions between some initial state, y naught, and some final state, y, and t. And I actually introduced not just one such transition probability, but two of them. So I call them t plus minus. And for them, the corresponding Langevin equations are shown here. So there's a plus and minus sign here, which differentiates these equations. Now, the reason I use that is because I'm going to use supersymmetry going forward. But for now, we can focus on just one of these one equations, namely the one which corresponds to the minus sign here, which is the equation corresponding to this initial Langevin dynamics. All right. But the way to solve them is common for both. So step number two, what we do is for the one equation, we change the variable, dependent variable, and we use this ansatz, which is shown here. And if you plug this expression into this for the one equation, you end up with the two Schrödinger equations in imaginary time, which are shown here. So, so the reason I call this volatility parameter h is actually can be seen here. H enters as h square enters as a Planck constant here, and because there is no imaginary unit, it's clearly showing the equation in imaginary time with this independence. All right. So, so what we can do, and what sometimes what people do to solve Schrödinger equation, you can use eigenstate decomposition, and if you have a set of eigenstates, psi minus f sub n with energies E sub n, then you can write down this eigenvalue decomposition for the solution of the Falkenberg equation, is the general, but if you only look at the asymptotic expression here, which survives when time goes to infinity, and the next pre-asymptotic term, then it will be only two terms in the sum, and we will get this expression, which is shown here. All right, so these all are very conventional stuff. So usually people solve this, they start with the potential, and they find first the stationary distribution and then the corrections, and then if they sum them up, then they get this. All right, but there is another way which actually was done, like the idea I got, of course, from physics, and people in physics, specifically people who did, like I saw it several times. One of them was in some research where people looked into supersymmetric quantum mechanics. And the idea is that instead of doing that, instead of following this conventional route of starting with the potential and then solving for that, they say, why don't we start with the defining this subset of parameterized ground state wave function, which is shown here. Right, and then we can derive everything from this wave function. So that's exactly what I did here. And I used a two-component, very simple wave function of the ground state, two-component Gaussian mixture, which is shown here. All right. Now, and everything else is actually derived from this. So I'll show you later how it's derived, but the potential corresponding to this ground state wave function is actually shown here, just the logarithm, negative logarithm of this wave function, scaled by parameter h and shifted by a constant. Right? So this thing, the stationary asymptotic distribution, can be thought as a fundamental input to model building. Why is it good? On many counts. One of them is that if you only want to, if you're only interested in the stationary solution of the model, then you're done. There is nothing to compute. That's already the answer. But if you want to compute dynamic corrections, then you can also do that, because specification of this specifies you the potential, and the potential specifies the rest of the dynamics. Right. So this one was actually inspired by the one of the most canonical examples in quantum mechanics, double well potential. which actually can be uncovered for some choices of the parameters here. So, and this is what is shown in this graph. So the first row shows you the different shapes of this ground state wave function for different parameter values. The second row shows you the square of this guy, and the last row shows you the potential obtained from this specification according to the formula that I just showed. Right. So and as you could probably expect, whenever you have like these bimodal distributions of the wave function, which translate into bimodal distribution of the stationary distribution of the Fokker-Clarke equation, which is given by the square of this guy, and then it translates into double well potentials, right? So I didn't show you examples of single well potentials here, but obviously it's one of the options. So you can have many different scenarios from this specification. All right. Now here's the reason why I use this two Hamiltonians and not one, is because I wanted to rely on supersymmetric quantum mechanics in order to simplify calculations of my eigenvalues and eigenvectors. Supersymmetric quantum mechanics was suggested by Ed Witten in '81 as a toy model to study supersymmetry in quantum field theory. And just 1 year later, Soviet physicists from Landau Institute discovered hidden supersymmetry of Langevin dynamics, which actually showed that Langevin dynamics is mathematically equivalent to supersymmetric quantum mechanics of Witten. And the reason this observation is useful is because of the following. So first of all, when you have supersymmetric quantum mechanics, it means that your Hamiltonians, this H1 and H plus and H minus that I showed you before, factorize into this product of first order operators, as shown here. And why it's useful is because when you have the Schrödinger equation for the ground state wave function, so this whole guy should act on the ground state wave function and get you zero, and this translates into a simpler equation because it's zero on the right hand side. We can cancel terms, and then this ground state wave function, equation, translates into the first order equation. That's the thing about that, right? So if it's a first order equation, then it's easy to solve, and you can just you can take the solution of this equation and invert it, and that's how you get this relation that I just showed you. All right, so the reason supersymmetry comes up very handy here is because supersymmetry relates the spectra of these two Hamiltonians and also relates the eigenstates as shown here. So what I technically did, I used this formalism in order to compute this correction that I showed you before. So my ground state wave function was actually omitted in my formulation, and then I used this SUSY-based formalism in order to compute corrections. But when I did it, I wanted to simplify it further and find some formulation which actually did not rely on the heavy machinery of supersymmetry, just by noticing that this first excited state, which is shown here for several combinations, actually looks pretty similar to the first excited states of harmonic oscillator, which is just a linear function times the Gaussian. And I just wanted to simplify this model further just by approximating this excited state, first excited state, computed from supersymmetric quantum mechanics by something simple like that. And this produced a drastic simplification of the whole framework. So this is the approximation that I used, right? And if I use this approximation and plug it back into the previous expression, I can simplify it even further. So the approximate expression would be like that, but like approximately again, when the correction is small, I can replace this expression by this expression, which buys me positivity of the whole expression because this guy is now positive. And then what I can also do is kind of subsume this exponential factor into the Gaussian distributions. Remember that psi naught was a two-component Gaussian mixture. When you square it, you get three-component Gaussian mixture. And when you multiply Gaussian mixture by this exponential term, you can rewrite it again as another Gaussian mixture, which is exactly what is done. All right. So the end result of this model is that we have a distribution of log returns approximated by a three-component Gaussian mixture. But the nice thing is that all parameters are now fixed in terms of my original parameters. That's what it buys. Right? You could otherwise you could start with this, but it would entail more free parameters. Right. Now, the last thing is that you can also, so that was the distribution for the real measure. What we need for option pricing is what is called the risk neutral distribution. And one way to construct one from another is to like, there are two names for this. Some people call it Asher-Keys form, and some other people call it minimum cost entropy method. It's essentially like if you can find the risk neutral distribution by assuming that it has the smallest scale divergence to your real measure distribution, and this gives you this formula, this exception, this relation. So, which tells you that the risk neutral distribution is again another exponential adjustment for a real measure distribution, right? Which I can write like that, but it again can be translated into a three-component Gaussian mixture, which now will serve as a model for log returns in the risk neutral measure. And because of that, because it's now a three-component Gaussian mixture, it's no surprise that the formula for European holes will be just a simple mixture of three Black-Scholes models, which is shown here. Right? But again, like I'm definitely not the first one who wrote a formula like that. There's been papers that did that, but it was the starting point from them. For me, it's the last one. That's the difference, right? So all parameters here are expressed in terms of my original parameters. All right, and now, so like the model can be calibrated to observe data. So my paper has examples of this calibration. Accuracy is pretty decent, I would say. Like when I calibrate to, like I can calibrate here separately for calls, so for puts and calls, which is the advantage of this model. Usually people like put them all together to calibrate, and inferred parameters are shown here. The interesting fact is that, and now I get this what I call implied potential, right? So implied potential is my potential where I use calibrated parameters to show what it implies. The interesting observation is that implied potentials for puts and calls are different. And I see this for both 1-month options, but also for options with longer tenor, like 1-year options. Again, something similar. Comparable pricing errors, comparable parameters, different potentials. Okay, but pay attention to that in these two examples, the potentials are all single-wire potentials. Right? Are there any cases when we have double potential? And I found a few examples of this sort. One of them is shown here. So for those of you who in business, you might remember that this day was day of extreme market volatility. So I wanted to look at what happens on this day. And surprisingly, I found that you see that now puts and calls convey somewhat different information. So similar and different. The difference is that this vertical line that I showed here was like you see that in the previous examples, this vertical line was actually the initial position of your particle, the starting log return, which was pretty much aligned with the bottom of the potential, with the minimum of this potential, right? In both these examples. It's not the case anymore on this date, right? So you see that this is clearly an indication that your dynamics is now non-equilibrium. You're far away from the location of the potential. But in addition, the second graph also shows that implied potential now is a double well potential, which brings back all these questions about whether metastability in the market is important and should be taken care of. And again, I would like to emphasize. Oh yes, I think I forgot to mention that. So what's non-perturbative? Non-perturbative are all methods which cannot be it's about effects which cannot be captured using either linear model or any sort of computation theory around linear models. So non-perturbative methods are methods which take these nonlinear effects as a kind of first-class citizens. And these results, I think, they show, or they give some support to the idea that non-linearities are foundational in finance, and we maybe better should think about building models where these non-linearities would be built in as part of the dynamics. And here's my short summary for this more general talk. So we would like quant finance models to be more explainable and avoid as much as possible approaches like quoted here. We consider the XYZ clause because it fits that data better. The second conclusion is that I personally believe that quant finance was focusing on kind of non-interest models, if you wish, right? So all the focus was on the diffusion term, while I gave you arguments that maybe the main focus should have been on the diff term, right? And for model building, we need non-equilibrium and non-perturbative models. And if we combine these insights from these two different disciplines, machine learning and physics, we can come up with something actually simple at the end. And this NES model, non-equilibrium skew model, just showed how it can be done in a simple way. And finally, I want to mention that this book that we published last year has a chapter that talks about multiple links between machine learning and physics, even involving something that I call grand unification of machine learning.